This is the Fall 2023 MA266 final exam. Go ahead and get started with question 1 here, which is a separable differential equation. That means we want to move all of our y's over to one side, all of our x's to the other, so that we can then integrate both sides. We'll multiply by root y to get root y dy, and by dx to make that equal to x plus 4 over root x dx. I'll go ahead and simplify this before we integrate. That'll be y to the 1/2 dy equals x over root x is just root x. I'll write that as x to the 1/2. And then 4 over root x is 4x to the negative 1/2 dx. We can integrate both sides here, and we will be left with y to the 3/2 with a 2/3 in front is equal to x to the 3/2, 2/3, plus 8x to the 1/2, and our plus c here will merge both of our plus c's over to 1 on this side. Now this is a solution here. None of them are in this form though. As you can see, it's going to match up with answer choice B. What they've just done is moved the 2/3 y to the 3/2 over to the right side and the c over to the other side. So we'll go ahead and make our solution look like theirs. We can subtract a c from both sides. We don't need a negative because c is just an arbitrary constant. And then we'll be left with 2/3 x to the 3/2 plus 8x to the 1/2 minus 2/3 y to the 3/2. And that does indeed match answer choice E. Number 2 is a first-order linear differential equation. You can rewrite this as y prime plus 3y equals 3x squared e to the negative 3x plus 2x e to the negative 3x to see that a little bit better. This means we're going to go ahead and find our integrating factor. Rho is going to be equal to e to the integral of 3 dx. We're getting that 3 from our coefficient on the y term there. Once we integrate this, that's going to get us e to the 3x, and now we go ahead and multiply everythy by that e to the 3x. So we will have e to the 3x y prime plus 3e to the 3x y equals 3x squared e to the negative 3x e to the 3x plus 2x e to the negative 3x e to the 3x. You can see these e terms are going to cancel out here because if we were to combine those using our exponential rules, that's just e to the 3x minus 3x, so e to the 0. So we can just rewrite this right-hand side as 3x squared plus 2x. This left-hand side, we can spot our product rule is just e to the 3x y all prime. We can now go ahead and integrate both sides. Once we do that, it'll leave us with just e to the 3xy on our left-hand side, and then the integral here is x cubed plus x squared, and remember your plus c. To isolate y, all we need to do is divide by e to the 3x. We'll end up with y equals e to the negative 3x times x cubed plus x squared plus c. Remember to keep your c inside that parentheses. Don't tack it on after you solve for y. And we can see that this choice does match answer choice B over here. In problem 3, we're being asked for an implicit solution to this differential equation. When we're asked to find an implicit solution to an equation that looks like this, there's a pretty good chance that it's going to be exact. We can go ahead and check that though, remembering that exact means dm dy is equal to dn dx, where m is this parentheses term here, and n is the term in parentheses here. dm dy is our partial derivative of m in terms of y, which is going to be 7, and dn dx will also be 7, so this is indeed an exact equation. Our solution to an exact equation is going to look like big F of x, y is equal to a constant c. Ultimately, what we want to do here is find a big F function such that its partial derivative in terms of x is equal to m, and that its partial derivative in terms of y is equal to n. You might have also heard this called a potential function or a gradient function. It's all the same thing, however you want to think about it. So we'll go ahead and start by integrating m in terms of x. So big F is going to be equal to the integral of 2x plus 7y dx. And that will get us f is equal to x squared plus 7xy. Instead of adding a constant c, we're going to add a function h in terms of y, because this could be anything in terms of a variable that's not x, which in this case is y, and it won't affect our derivative. So we now go ahead and take the partial derivative of big F in terms of y, and we know that we need to get that to be equal to n. So f in terms of y is equal to 7x plus h prime of y. And we see in order to make this match up here, we need h prime of y to be equal to 8y. Integrating that gets us h of y has to equal 4y squared. We can take this now and plug that h into our original big F function and get f equals x squared plus 7xy plus 4y squared. And when we write that in our implicit form equal to a c, we'll get x squared plus 7xy plus 4y squared is equal to c, which does indeed match answer choice A. Another good way to spot that this was an exact differential equation, if it wasn't quite as obvious as they wrote it here, is that all of our answer choices are equal to c. Sometimes you'll have problems where it's not super clear it's an exact differential equation, but if every option has something in terms of x and y equal to c, there's a pretty good shot it's an exact differential equation.
In problem number 4, we're being asked to sketch typical solution curves to this given differential equation here. The first thing we need to go ahead and do is set up our phase diagram. So go ahead and draw out a number line, and we need to find our roots of this equation. So if we set 2y squared times y minus 1 equal to 0, you can pretty clearly see that from this first y we'll get a 0, and from this y term in the parentheses we'll get a y is equal to 1. That's what makes our differential equation equal to 0. So go ahead and make marks for those two roots on our number line. We need to go ahead and start checking points now. We need to check some point less than 0, some point between 0 and 1, and some point greater than 1 in order to get the full picture here. So pick a point below 0, we'll pick negative 1. We're going to have 2 times anything squared is always going to be positive. This will become 1 squared. And then this parentheses term is really what we care about, because that's the one that can change. Negative 1 minus 1 is negative 2. That whole thing is going to be negative, so everything below 0 is decreasing. Between 0 and 1, we'll go ahead and pick a half. 2 times, again, anything squared is positive. We can ignore that first part. Y minus 1, 1 half minus 1 becomes negative 1 half. And then that's going to make this entire expression negative, so that middle part is also negative. Pick something greater than 1 now, we'll pick 2. We'll get 2 times 2 squared, that gets us 8, and then times y minus 1. 2 minus 1 is positive 1, so this part here will be positive. We can go ahead and draw our arrows in here, going to the left where we're negative, and to the right where we're positive. You can see we're going to have an unstable equilibrium here at 1, and our graph should just pass right through 0. We can go ahead and start checking this against our graphs that we're given now. We're looking for something that's decreasing below 0 and between 0 and 1, and something that is increasing as we move to the right greater than 1. Let's take a look at A here first. We see that above 1 we are indeed increasing, between 0 and 1 we are indeed decreasing, but below 0 we are increasing as we move to the right here, so A is not our correct graph. 2, right away we see that we're decreasing in our range above 1, so B cannot be the correct graph either. C, we are increasing above 1, we are decreasing asymptotically between 0 and 1, and then we are decreasing below 0. So this matches our phase diagram here, so C is indeed our correct graph. We can also go ahead and check here why D and E are incorrect. D has 0 to 1 increasing, that's wrong, and E has... what's wrong? E here, between 0 and 1, is increasing, which it should be negative. That leaves just C as our correct answer. Problem number 5 is a pretty typical IVP. we're given our differential equation here and two initial conditions in y and y prime. Let's go ahead and plug in our r's and find our characteristic equation. We'll get r squared minus 4r plus 4 is equal to 0. That factors nicely into r minus 2 squared is equal to 0, and that gets us r is equal to 2 with a multiplicity of 2. We can go ahead and write out our general solution now. So we'll get y is equal to c1 e to the 2t, just like we normally would. And then because we have this repeated root, our next term we multiply by t, our independent variable. We'll get c2 times t e to the 2t. Again, that's because we have this 2 repeated root here. This is our general solution, but we're given these initial conditions up here. One of them is in terms of y prime, so we'll go ahead and find y prime now. Y prime is going to be equal to, when we chain rule, we'll get 2c1 e to the 2t. And then remember to do product rule on this because we have both the t term and the e to the 2t term. So we'll get a c2 e to the 2t, and we'll get a 2c2 times t e to the 2t. We can go ahead now and start plugging in for our initial conditions. So using our y expression, we get 12 for y is equal to y of 0. When we plug 0 in for our t's, we're going to be left with just c1 because e to the 0 is 1. And then plus, this term will actually fully disappear because this t will become 0. For our y prime, we can start plugging in. We see our left-hand side is going to be negative 3 is equal to, then plug 0 in for t. We'll get 2c1, again, the e to the 2t will just become a 1, and then plus just c2, again, same reason that e to the 2t disappears, and then our last term is going to fully disappear because of this t here is going to become 0. We know our c1 is 12, so we can go ahead and plug that in. Negative 3 is going to equal 24 plus c2. Solve for c2, that will get us negative 27 is equal to c2. We can go ahead and plug this back into our general solution now that we have our c values, and get that y of t is equal to c1 is 12 e to the 2t plus, or that'll be minus 27 from our c2 term over here, t e to the 2t. And we go ahead and compare that with our answer choices. We'll see that matches answer choice B here. Problem number 6 is a variation of parameters problem. So we are given a differential equation, and we're given its complementary solution and asked to find the particular solution using variation of parameters. Remember that when we're using variation of parameters, we're always looking to take this complementary solution and turn it into something like y of x equals u1 y1 plus u2 y2, where we can then use our known y functions and solve for our two u's, which are functions instead of constants, like when we do our constant c's here. So we are clearly given our two y's as x squared and x cubed. So we'll write y1 is equal to x squared, and y2 is equal to x cubed. Before you start with variation of parameters, though, the important thing is to make sure that the coefficient on the highest order term of your differential equation, so this, is 1. This will get you because you'll make mistakes. You'll forget to divide everything out by x squared. Your answer will seem fine, but it will just be entirely wrong, and you will not catch it. So we're going to do that right off the bat here. We're going to divide this entire equation by x squared to get a coefficient of 1 there. So that'll leave us with y double prime minus 4 over x y prime plus 6y over x squared equals x. And then we call this right side of our function f, so we'll write f equals x. You can notate that however you want, however you remember your variation of parameters formula. So we are given our f, and then we know our two y solutions that we linearly combine to get our complementary solution. So we can write y of x is equal to u1, and then y1 we defined as x squared, and u2 times x cubed. Again, I'm just rewriting essentially this replacing our constants for these unknown functions u. We can now go ahead and start using our variation of parameters formula. The first thing we need to do is find our Wronskian. Remember, your Wronskian is equal to the determinant of y1. I'll write this out over here. W is equal to y1, y2, y1 prime, y2 prime, the determinant of that. So y1 is x squared, y2 is x cubed, the derivative of x squared is 2x, the derivative of x cubed is 3x squared. To take a determinant, remember, you're going to multiply those two terms and subtract the product of those two terms. That will leave us with 3x to the fourth minus 2x to the fourth, which comes out nicely to just x to the fourth. Now, using Cramer's rule, you can derive this with Cramer's rule, or I suggest just memorizing that in variation of parameters, your u1 is always equal to negative integral of f times y2 over the Wronskian, and u2 is always equal to the positive integral of f times y1 over the Wronskian. I like to think of this as f just replacing the y1 function here because it's u1, f replaces y1, but remember that however you want. Also remember the negative in front of u1, not in front of u2. We now have everything we need to go ahead and start plugging in here. So u1 is equal to negative integral f, we defined up here as x, and we defined y2 as x cubed. So x times x cubed over x to the fourth dx. You'll see that this is going to come out nicely as x to the fourth over x to the fourth. So negative integral of 1 dx, that's equal to negative x. We'll go ahead and do the same for u2. That's going to be, from our formula here, f is x, and y1 is x squared. So x times x squared over x to the fourth dx. That will get us x cubed over x to the fourth, which is the integral of 1 over x dx. That integral comes out to ln x. You don't need to include a plus c in these integrals here. So we found u2 is equal to ln x, and u1 is equal to negative x. We can now go ahead and plug this back into our original formula up here. So y of x is equal to u1, which is negative x times, we already identified that our y1 is x squared. You can also just plug it straight into here. It's the same thing, times x squared. And then plus u2 is ln x times our y2 function, so times x cubed. This will get us negative x cubed plus x cubed ln x. Factor out an x cubed from there, and reorder the terms on the inside. We'll get x cubed times ln x minus 1, and that is yp of x, our particular solution. And that does indeed match answer choice E in the options. Number 7 is another non-homogeneous initial value problem. Remember that when we have a non-homogeneous IVP like this, we're looking to write our solution, y of x, in the form y complementary plus y particular. We can easily find the complementary solution, and we need to decide to either find the particular solution through variation of parameters or undetermined coefficients. Because we have a pretty nice right-hand side here that we can make a nice guess for, we'll use undetermined coefficients. That's usually the faster method when we can use it. We'll start with our associated homogeneous to find our complementary solution. So go ahead and create our characteristic equation, r squared minus 3r minus 4 equals 0. That factors nicely into r minus 4, r plus 1, and that gets us r is equal to 4 and negative 1. We can take those and write out our linear combination. So y complementary is equal to c1 e to the 4x plus c2 e to the negative x. We now have the first part of our solution. We need to find the particular part. What we'll do for undetermined coefficients is go ahead and make a guess for what the form of our y particular will have to be. Because our right-hand side here has an e to the 2x, we know that somehow our yp is going to have to be something times e to the 2x in order to get anything of that form. When we make this guess, we're also going to go ahead and check. We're going to go ahead and check against our complementary solution and make sure none of the terms match in form. So we have an e to the 2x here. Here we have a 4x and we have a negative x. None of those are e to the 2x, so we're good. We don't need to change our particular solution guess at all. We can differentiate and find that y particular prime is equal to 2a e to the 2x, and yp double prime is equal to 4a e to the 2x. Well, now I'll go ahead back to our original differential equation and plug in our guess for yp. So y double prime is going to get this yp double prime going into there. So do that down here. 4a e to the 2x, and then minus 3 times yp prime, so minus 3 times this. That'll get us minus 6a e to the 2x, and then minus 4 times yp will be minus 4a e to the 2x. And this is our non-homogeneous part, so we leave our right-hand side as 3e to the 2x. Our first and last term here will cancel, and we get negative 6a e to the 2x is equal to 3e to the 2x, which gets us that a is equal to negative 1/2. And that means that yp, if we go ahead and plug that back into our original guess up here, has to be equal to negative 1/2 e to the 2x. So now we have both our y complementary and our particular solution. We can go ahead and add those to get our general solution, or our solution to the IVP, rather. So y of x is equal to c1 e to the 4x plus c2 e to the negative x. That's coming from our complementary solution right there. And then we're adding our particular solution, which we found to be minus 1/2 e to the 2x. Now we can go ahead and start solving for our c's here. Don't make the mistake of doing that at this step. We need our non-homogeneous part, otherwise you'll get incorrect values for c and it won't work out. We're going to need y prime in order to use that initial condition, so we'll go ahead and differentiate here. Y prime is equal to 4c1 e to the 4x minus c2 e to the minus x, and then that'll be minus e to the 2x. We can go ahead and plug in our first initial condition. We're going to get 5/2 is equal to c1, that'll become e to the 0 is just times 1. Same thing on this one, c1 plus c2, and then minus 1/2 times e to the 0 is 1, so c1 plus c2 minus 1/2 is equal to 5/2. And then for our y prime, we'll get a 1 on the left-hand side, and when we plug in 0, we'll get 4c1 times 1 minus c2 minus e, oh wait, that'll become a 0 as well. Or sorry, that'll become a 1. E to the 2 times 0 is e to the 0, which is 1. So what we have here when we rewrite our system is 6/2, that's just 3, is equal to c1 plus c2. And then this will become 2 is equal to 4c1 minus c2. Go ahead and solve this however you want. I'll just add these together and get 5 is equal to 5c1 plus 0. So c1 is equal to 1. If we plug that back into our first equation, we'll see that c2 has to be equal to 2. We'll take this now and plug into our general form here and get that y of x is equal to c1 is 1, so e to the 4x, plus c2 is 2, e to the negative x, minus 1/2 e to the 2x. We can go ahead and check that against our different options for solutions here, and we'll see that this matches choice D here. So this is your final solution to this non-homogeneous initial value problem. Problem number 8, we're given a mass spring system whose motion is defined by this differential equation with these initial conditions, and we're asked to find its amplitude. So the first thing we need to do is go ahead and solve the actual differential equation, and from there we can pick out the amplitude. So plugging in our characteristic equation, we'll get r squared plus 100 equals 0, r squared is equal to negative 100, and that gets us imaginary solutions of r is equal to positive or negative 10i. When we have imaginary solutions in this form, we'll write our general solution as u of t is equal to c1 cosine 10t plus c2 sine 10t. And then we can go ahead and take the derivative of that because we'll need that in order to plug in our initial conditions into this general solution to get our particular solution. So u prime of t is going to be equal to, pulling out the 10, that'll get us negative 10 c1 sine 10t plus 10 c2 cosine 10t. We can go ahead and substitute in our initial conditions now, and we'll get 2 is equal to, we'll keep our cosine term because cosine of 0 is 1, so 2 is equal to c1 plus this entire term will become 0 because of the sine of 0 is 0. And then for u prime, we'll get negative 10 is equal to, again, we'll lose our sine term because sine of 0 is 0, and cosine of 0 is 1, so this will just be 10c2. Solving that for c2, we get c2 is equal to negative 1. We can now go ahead and plug this back into our general solution. So we get u of t is equal to c1 is 2, so 2 cosine 10t minus 1 from our c2 value right here, sine of 10t. Now this is our solution to the differential equation, but this doesn't really help us with the amplitude because we've got two terms here. So we need to use an identity to combine these into one cosine term, and we can turn this into an equation of the form r cosine omega t minus phi. We don't care about any of this cosine part though, because the maximum that can be is 1, so we know that our amplitude is just going to be this r value. And this r is always equal to the square root of your c1 squared plus your c2 squared when you write your differential equation in this form, of course. It's these coefficients that we're using there as our c's. So our r is going to be equal to the square root of 2 squared is 4, minus 1 squared is 1. R is equal to the square root of 5, and therefore our amplitude is root 5, which is option A. Number 9 is a salt tank problem. Remember, in these problems, we're always going to set up our differential equation as dx dt, where x is the amount of solute in our tank, is equal to the rate in times the concentration in, minus the rate out times the concentration out. We can go ahead and start pulling off values from our problem. I also always like to check that our units all just match up. They're not giving us something in seconds and something in gallons, but here we seem to be fine. So rate in, we can skim through our statement. Salt solution with the concentration is added to the tank at a rate of 2 gallons per minute, so rate in is equal to 2. And we just saw that our concentration in is equal to 6 grams per gallon. Our rate out, we're given right below that, is also 2 gallons per minute. And our concentration out, remember that this is all getting well mixed in the tank, so our concentration out is going to be the amount of solute over the volume in the tank at that time. The amount of solute is just x. And the amount in the tank, we're starting with 10 gallons and then adding 2 gallons per minute, but also removing 2 gallons per minute. So we're just staying constant at 10 gallons in the tank at all times. We can go ahead and start plugging this in to solve our problem now. dx dt is equal to rate in times concentration in gets you 12, minus 2 times x over 10 is x over 5. Go ahead and rewrite this with all our x terms on one side, and I'll write this as x prime plus 1/5 x is equal to 12. And we can see now pretty clearly that's a linear differential equation. We can go ahead and find our integrating factor. Rho is equal to e to the integral of 1/5 because that's the coefficient on our x term, dt, and that gets us e to the t over 5. That's written weirdly, t over 5. Great. We can go ahead and multiply everything by that. We'll get e to the t over 5 times x prime plus 1/5 x times e to the t over 5 equals 12 e to the t over 5. We can see our product rule on the left-hand side. that's just x e to the t over 5 prime is equal to 12e to the t over 5. And if we integrate both sides, we'll get x e to the t over 5 is equal to the integral here, pull down the 5, is going to be 60 e to the t over 5 plus c. Remember your plus c there. We now need to go ahead and isolate x, so we'll divide both sides by e to the t over 5. That'll cancel out on this 60 term, and then leave us with 60 plus c over e to the t over 5. We're now given our initial conditions, but we're not given directly what we need. So we know at t equals 0, the amount of solution in our tank, we're not given the actual amount of solution, we're just given that there are 10 gallons with 3 grams per gallon. So our concentration is equal to 3 times 10. So our x of t, or that should be x of 0, is equal to 30. We can use that given initial condition to go ahead and actually solve for our c here. So we know that 30 is equal to 60 plus c over e to the 0 is 1, and that shows us that c is equal to negative 30. We can go ahead and plug this back into our general solution and get x of t. I'm just pulling this from right here. Plugging in gets us x of t is equal to 60 minus 30 over e to the t over 5 power. And then it's asking us to find at t equals 10 how many grams of salt are in the tank. So we'll go ahead and plug in 10. That'll get us 60 minus 30 over e to the 10 over 5 is e squared. Let's go ahead and take a look at our answer choices. We have, that looks like it'll match answer D. They just wrote it differently. In number 10, we're asked to find the appropriate form for a particular solution of this differential equation. When we get a question like this that's only asking us for the form and not to actually solve it, we know that they're going to be checking if we know how to deal with duplication in the terms, so that's what we're watching out for. We'll go ahead and solve our associated homogeneous first. So set up our characteristic equation as r cubed plus 4r squared plus 4r is equal to 0. Factor that into r times r squared plus 4r plus 4. And that factors one more time into r times r plus 2 all squared. From there, we see that r is equal to 0 or negative 2 with a multiplicity of 2. We can set up our complementary solution then as y complementary equals c1 e to the 0, so just c1 plus c2 e to the negative 2 plus c3 x e to the negative 2x. That should be an x there. This x is just coming from the fact that it's a multiplicity 2. That's how we deal with our second term there. We can now go ahead and find our initial guess for the right-hand side. So pulling from this function here, we know there are two parts of this. There's the e to the negative 2x part and the x part. E to the negative 2x is just going to be there how it is. And then from x, we need both the x term and all the lower order terms. So we need an ax and a b. And then we know that this can be distributed to get us combinations of both. We'll go ahead and distribute this out so that we can check for duplication with ax e to the negative 2x plus b e to the negative 2x. And now we can go ahead and compare these terms with the terms of our complementary solution. We see here we have an e to the negative 2x term. We also have an x e to the negative 2x term. So both of those terms are problematic. To deal with that, we'll go ahead and multiply by our independent variable. So this will become ax squared e to the negative 2x plus bx e to the negative 2x. We can go ahead and check again. This term's good because there's no x squared term up here, but this term is still problematic because we still have it matching the x e to the negative 2x term. We'll go ahead and multiply by x one more time, get ax cubed e to the negative 2x plus bx squared e to the negative 2x. And now none of these terms match the form of any up here. They're all higher orders. So we can go ahead and take this as our form of the particular solution, and this will match answer choice B. We're asked to find which of the following functions is a potential solution to this homogeneous differential equation. Because it's homogeneous, we'll set up our characteristic equation, r to the 4 minus 16 is equal to 0. You can factor this into r squared plus 4 times r squared minus 4. And then again into r squared plus 4 times r plus 2, r minus 2. From this r squared plus 4, we need that to be 0. That's obviously going to get us imaginary solutions because we'll have r squared is equal to negative 4. We get that r is equal to plus or minus 2i from that term. And then from r plus 2 and r minus 2, we just get r is equal to plus or minus 2. We can now go ahead and start writing out our general form of our solution. So y is equal to c1, we'll start with our real solutions, e to the 2t, plus c2, e to the negative 2t. And then for our imaginary part, there's no real constant in front of this, so this is just going to be plus c3 cosine 2t plus c4 sine of 2t. And now in our answer choices, they actually plugged in values for this. Remember, these c's are all just arbitrary constants, so they can take on any value. We just need to figure out which form matches. In A, they have cosine and sine of just t, which is incorrect. We need 2t. Same in B, they have 4t. C does have cosine of 2t, sine of 2t. And then they have an e to the 2t and an e to the negative 2t term, so that all matches. So C is our correct option here. Keep in mind they could always throw in a solution where one of your c's is 0. Just watch out for that. In problem 12, we're given a linear system of differential equations and asked what the phase portrait will look like at the origin. To do this, we need to find our eigenvalues. So we'll go ahead and set that up. Subtract lambda from your main diagonal of the matrix. And then take the determinant of that. Remember, your determinant is the product of these times the product of that diagonal, or sorry, minus the product of that diagonal. That'll get 4 minus lambda times negative 1 minus lambda minus 6. You can rewrite this as minus 4. That'll be plus lambda minus 4 lambda, so minus 3 lambda plus lambda squared minus 6. And these can combine into lambda squared minus 3 lambda minus 10. We can go ahead and factor this into lambda minus 5 lambda plus 2. And that gets us lambda values of 5 and negative 2. We have two real eigenvalues, one positive and one negative, which means that this is going to be a saddle point. You just need to memorize what your combinations of eigenvalues mean in the case of phase portraits. Number 13 is a system of differential equations with initial values. Here it's written as in the form x prime equals ax. So we need to go ahead and first find our matrix for A. We'll just pull the coefficients off of these equations, so we'll get 6, negative 3, 2, and 1. We need to go ahead now and find the eigenvalues of this matrix. So we'll set up the determinant of the matrix, subtracting lambda from the main diagonal. And remember, your determinant is equal to this, the product of those two terms, minus the product of those two terms. So 6 minus lambda times 1 minus lambda minus negative 6 is plus 6, and we're setting that equal to 0. Can multiply this out to become 6 minus lambda minus 6 lambda is minus 7 lambda plus lambda squared plus 6, and we can rewrite that as lambda squared minus 7 lambda plus 12 is equal to 0. Factor that into lambda minus 4 times lambda minus 3, and that gets us eigenvalues of 4 and 3. We now need to go ahead and start finding the associated eigenvectors for each eigenvalue. We'll start with lambda is equal to 4. Remember, we go ahead and plug our eigenvalue in for lambda in this matrix first. So we'll write that as 6 minus lambda is 6 minus 4, so 2, negative 3, 2, and then 1 minus 4 is negative 3. And we're looking for a vector AB that we can multiply that matrix by that results in the 0 vector. We can go ahead and multiply out our matrices and get 2a minus 3b is equal to 0. The second one will also be 2a minus 3b is equal to 0. These should always simplify to be the same equation. The easiest solution to pick here for a and b is a is equal to 3 and b is equal to 2, because that satisfies both of these equations. Now we can go ahead and work with lambda equals 3. When we subtract that from our main diagonal, we get 6 minus 3 is 3, negative 3, 2, 1 minus 3 is negative 2. Multiply by our unknown a and b, and set that equal to the 0 vector. If this step wasn't clear, I'm just taking this matrix and subtracting our lambda, plugging our lambda in for those lambdas and subtracting. Multiplying this out gets 3a minus 3b minus 3, I can't write, 3b is equal to 0, and 2a minus 2b is equal to 0. So a and b have to be equal. The easiest vector to pick here is just 1, 1. We can go ahead now and write out the form of our general solution. So that'll get us x of t is equal to c1 times our first eigenvector, 3, 2, times e to the 4t. This 4 is coming from the associated eigenvalue that goes with this eigenvector. And then same thing for the other one, c2 times 1, 1, e to the 3t. This is the general form of our solution. We have initial values to plug in though, so we're going to go ahead and find our particular solution. We know that 5 and 3, we'll write that here, 5, 3 is our solution when t is equal to 0. So equals c1 times 3, 2. E to the 0 is just 1, so that disappears. Same thing in this term, so we're just left with c2 times 1, 1. We can write this as a system of two separate equations. 5 is equal to 3c1 plus c2, and 3 is equal to 2c1 plus c2. Subtracting the bottom from the top equation gets us 2 is equal to c1. If we go ahead and plug c1 back into either of these equations, plug into the bottom one, we'll get 3 is equal to 4 plus c2. So c2 is equal to negative 1. We can go ahead now and plug that back into the general solution form to get the particular form. Get x of t is equal to c1 is 2, 3, 2, and then c2 is negative 1, so minus vector 1, 1, e to the 3t. We can see all the forms here, they've separated it out into two different equations, so x is always going to be the top half of this equation, and y is the bottom half because of the way they've set it up here, looking back to the original problem. So we'll go ahead and multiply out and split into those two equations. So we'll get x of t and y of t. Or actually, I'll just write these as two completely separate equations. X of t now is just the top piece. So multiplying out along the top here, we're going to get 6 e to the 4t minus e to the 3t. And then the bottom part of that will be y of t equals 4e to the 4t minus e to the 3t. We can go ahead and check this against our options for solutions here. And it looks like this is going to match option C. For number 14, we need to use the method of matrix exponentiation, where we remember that e to the at is equal to phi of t times phi inverse of 0. So here phi is our fundamental matrix, so it's our set of fundamental solutions. Think of this as the two terms that we linearly combine to get our general solution. So that means phi is equal to the matrix v1, so eigenvector 1, times e to the lambda 1t, and v2 e to the lambda 2t. So here they give us both of our lambdas and both of our eigenvectors, so we need to go ahead and plug that in. We get that phi is equal to v1 is 1. Actually, we'll write this as columns of a matrix, so or rows of a matrix. So 1 times e to the lambda 1t, so e the negative 3t, and below that we'll have negative 1 times e to the negative 3t, and then pulling from v2 and lambda 2, we will get 3e to the 4t and negative 2e to the 4t. We can go ahead now and find the inverse of this. Remember that the inverse of a 2 by 2 matrix, or actually we'll plug in 0 first, that'll make this a lot easier to find the inverse without doing it symbolically. So phi of 0 is equal to e to the negative 3 times 0 is just 1. Negative 1 times e to the 0 is just negative 1. 3 times e to the negative 0 is just 3. And this last one is just negative 2, which means the inverse is equal to 1 over the determinant times negative 2, 1. Remember, we swap those two terms, and then we negate the other two terms, so 1 and negative 3. The determinant of this matrix is these two terms minus those two terms, so that's negative 2, I'll write that here, det of phi is equal to negative 2 minus negative 3, so it's just equal to 1. So this determinant doesn't actually change at all. We're just dividing everything by 1, so it stays negative 3, or negative 2, negative 3, 1, 1. We can go ahead now and move this out of our way, and we can multiply these matrices out. So we have phi of t, so that is this matrix. I'm just going to copy it down and simplify a little bit. E to the negative 3t, 3e to the 4t, negative e to the negative 3t, negative 2e to the 4t. And we're going to multiply that by our inverse at 0, at t equals 0. So that times negative 2, negative 3, 1, 1. When we do our matrix multiplication, we go ahead and multiply row times column first. So negative 2 e to the negative 3t plus 3e to the 4t. We'll go ahead and do our second row times our first column. That will get us 2e to the negative 3t minus 2e to the 4t. And then our first row times our second column gets negative 3e to the negative 3t plus 3e to the 4t. And then our second row times our second column is 3e to the negative 3t minus 2e to the 4t. None of these are like terms, so none of them simplify at all. So let's go ahead and just check these against our answer choices. It's not any of these. And when we go compare with our solutions, it looks like this does match answer choice D. This problem is asking us to find the form for the particular solution to this non-homogeneous system. The first thing we'll do is solve the associated homogeneous. So we'll set this up like we normally do and find our eigenvalues first. So subtract lambda from the main diagonal. Multiply your main diagonal and subtract your other diagonal and set that equal to 0. This will multiply out and get us lambda squared minus 2 lambda. It'll be plus 1 minus 4 is just minus 3. And this factors into lambda minus 3 times lambda plus 1 is equal to 0 and gets us eigenvalues of 3 and negative 1. We don't actually need to go ahead and find the eigenvectors like we normally would, because we can just represent them symbolically as v1 and v2. It won't matter when we're checking for duplication because we're not asked to find the actual solution here. So we'll go ahead and set that up as x. The complementary solution is equal to c1 times our unknown eigenvector 1 times e to the 3t plus c2 eigenvector 2 times e to the negative t. Now we need to go and start guessing our particular solution form and check against this for duplication. We know that if they're asking us just define the form, there's probably going to be duplication. So looking at the non-homogeneous term, we see that we're going to need a term in the form vector A times e to the t, and we're going to need a term that's vector B e to the negative t. I should write this as equal to y particular. We go ahead and check these terms against our complementary solution. This term's fine, there's no e to the t term, but this term has duplication with that term. So we need to multiply by t, but because this is a system, we also need to include all of the lower terms. Our a e to the t will stay. Because it's a separate term, that one is left alone. And then we'll get a b plus vector c t e to the negative t. Again, we need to include this b term here because it's a system. If this was just a single solution or a single differential equation that we were asked to find the form for, we would not need this lower term, but you always need to include it when you're solving a system. We can check again for duplication. This e to the t term is still fine. And now we know that there's no t e to the negative t term in any of our complementary solution terms here, so we are good to go ahead with this form. We can check this against our potential solutions, and it looks like they wrote slightly different vector letters than we did, but this matches answer choice E. This problem is our first Laplace problem. We're given an initial differential equation here, and we're told that when taking the Laplace transform of it results in this expression, and we need to find constants a and b, such that this is our final result. So we'll go ahead and take the Laplace transform of our initial function here. Because Laplace transforms are linear functions, we can split it up term by term. So we'll get Laplace transform of x double prime, plus we can pull out our constant a, times Laplace transform of x is equal to pull out the b times the Laplace transform of t cubed. I hate that s's are what they use for Laplace transforms because I think they look too much like 5s. Sometimes I'll switch to using q instead. I'll stick with s for now and just try to be really clear if it's a 5 instead of an s. So we can take a look at our table of Laplace transforms. X double prime, take a look at number 18, which gets us a function to a certain derivative. Here n is equal to 2 because it's x double prime, x to the second derivative. And referencing our function there, we see that the Laplace transform of that is going to be s to the n, so s squared times big X of s minus s, because this is s to the 2 minus 1, times our initial condition x of 0, so that's times 1, so that's just s, and then minus s to the 0 is 1, so 1 times our initial condition x prime of 0, but that's just 0, so we lose this term. We can move on to our a term now, keep the a out in front, and the Laplace transform by definition of little x is big X. That's just our notation for the Laplace transform of a function s. Then keep our b out in front, and the Laplace transform of t cubed go to number 3 on the sheet. That gives us t to the n, here n is 3. So that's 3 factorial, which is 6, over s to the n plus 1, so s to the 4. We'll go ahead and try to isolate our x's, so we'll keep all these terms on one side, we'll move the s over to the right, and I'll factor out the x term. So let's start on the left here. Factoring out the x from the two terms with that, we'll get times s squared plus a, and then moving this single s over to the right-hand side, we'll get 6b over s to the 4th plus s. We can go ahead and divide both sides by this term now to isolate big X. That'll get us x of s is equal to 6b over s to the 4th times s squared plus a plus s over s squared plus a. And now we need this side to look like this. So we need to get a 1 over s term and a 1 over s to the 6th term. Obviously, the s to the 6th term is going to have to come from this part because there's no way we can get an s to the 6th on the bottom there. But when we multiply these two terms, we'll get that s to the 6th. It's a tongue twister. And then on this right-hand side, we'll get our just 1 over s term, because these s will cancel with one of those. So for that to work, on the right-hand side, on the bottom here, we need that to just be an s squared. And here we need that to just be an s to the 6th. So a is going to have to be equal to 0, because that would get us 6b over s to the 6th plus, or that'll just be 1 over s, because it would be s over s squared. So now we're good with this term. That matches that. This term needs to look like this. So we just need to cancel out that 6 with the b. So b is going to have to be equal to 1/6, because that'll get us the 1 on top. So a is equal to 0, b is equal to 1/6. That is answer choice B. Number 17 is asking us to find the inverse Laplace transform of this function here. So essentially what we're trying to do is somehow rewrite this function in a way that it matches either one or more than one Laplace transforms on our sheet, so that we can then work backwards and get little f of s. A good place to start with these, especially when you have a form that looks like this, is by completing the square of your denominator. So we'll write that off to the side here. We have s squared minus 4s plus 29. That's going to have to be s minus 2 squared in order to get this s squared in the minus 4s term. That'll leave us with a 4, and we need to get to 29, so that'll be plus 25. Let's go ahead and swap this in for our denominator. We won't write anything in the numerator just yet. So that's s minus 2 squared plus 25. And now when we're looking at our table of transforms, this is starting to look like the denominator of our sine and cosine functions in numbers 9 and 10, the offset ones with the e to the at in front. But we know for this to work, we're going to need this s minus 2 to be uniform everywhere. We can't really have an s minus 2 down here and then an s somewhere else in this form, at least with most of the forms that we know how to get their inverse transforms. So we need on the top to also be an s minus 2 in order to nicely match the bottom there. So we're going to write this as, we still need the 4s. So 4 times, we'll write our s minus 2 there, and that'll leave us with s minus 8, but we need it to be a minus 3, so we just need to add 5 to keep that equal to our original function. Now this form is probably starting to look more familiar. What we can do is go ahead and break this apart into 2 different fractions, just by fraction addition. So split it at your numerator, you get 4 times s minus 2 over s minus 2 all squared plus 25 plus 5 over s minus 2 squared plus 25. Now this should start to look a lot like your sine and cosine forms, numbers 9 and 10 on your Laplace transform sheet, and that is exactly the form that we have here. So starting with this first term, we have 4 times, we can pull out the 4 in front, so that's 4 times s minus 2 over s minus 2 squared plus 25. And that is number 10 on the sheet. So that's e to the at cosine b of t. So our a here is equal to 2. And b here is equal to the square root of 25, so 5. So this term is going to be e to the 2t, e to the at, times cosine of bt, so cosine 5t. We can work with the second term now. That's very similar, but this is our sine function because we don't have the a, or we don't have the s minus a on top, it's just a b term. And we can see that the 5 and the 25 do match, because here our 5 is b, and then 25 is b squared. If those didn't, we could always factor out a constant to make it match, though. So I'll just rewrite this down here. And here b is still 5, a is still 2. So this is going to be plus, looking at the sheet, e to the at, so e to the 2t sine bt, so sine of 5t. And now we can go check this against our answer choices. And it looks like, oh, I forgot to pull down our constant 4 here. We pulled that constant out in front, so that comes down here. And now this matches answer choice D. Here we're given an initial value problem, and both because it's question 18 in the last section of the exam, and because we see this delta function here, we know we're going to have to use Laplace transforms to solve this. So we can go ahead and start by taking the Laplace transform of our differential equation. We'll get Laplace transform. Actually, I'm not going to write out this step. You've done this already. The Laplace transform of x double prime. Take a look at number 18 on your sheet. That's going to be s squared times big X of s minus, we would have s times this term, but that's a 0, so we lose that. And then we get s to the 0, so 1 times our x prime term at 0, so that's minus -1 is plus 1. Then our transform of little x is just big X by definition. And then on our right-hand side, go up to number 3, we have t to the 1, so that's 1 factorial, which is just 1 over s to the 1 plus 1 is s squared. And then we have our delta function here. That is on your table at number 17. Here c is equal to 2 pi, so the transform of that is just e to the negative 2 pi s. Now we need to start isolating our big X, so we'll move this 1 over to the right-hand side and we'll factor out these x's. So we'll get big X. I'm going to stop writing the of s, but remember that big X is a function, times s squared plus 1. The 1 is coming from there, and then we're going to move this term over to the right-hand side. So that will become 1 over s squared plus e to the negative 2 pi s minus 1. We'll go ahead and divide by this term. Big X is equal to 1 over s squared times s squared plus 1 plus e to the negative 2 pi s over s squared plus 1 minus 1 over s squared plus 1. So these two forms are looking pretty familiar now. Those we would know how to take the inverse transforms of. This term is our problem here. Because we have these nice two terms on the denominator, though, we know we have to partial fractions it. You could go through and do your actual whole partial fractions, but because this is a simple case, to save some time, what I like to do is just start with 1 over s squared plus 1 over s squared plus 1, and then go ahead and get your common denominator, figure out what that comes out to. So that'll be s squared plus 1 plus s squared all over that common denominator. We know that we want these s terms to cancel instead of adding, so we need to change this to a negative. That would change this to a negative, and that'll leave us with 1 over the common denominator. If you want to go through the actual partial fractions process, you can, but this one's a little annoying because of the squared terms on the bottom. Do that if you want, it just takes more time. So we'll go ahead and bring that down here now. X is equal to 1 over s squared minus 1 over s squared plus 1. Those are both from that first term. And then I'm going to write them in a different order to make this a little clearer. Now we see that we have two like terms there. So we can write this as 1 over s squared minus 2 over s squared plus 1 plus e to the negative 2 pi s over s squared plus 1. These first two terms are pretty straightforward to get your inverse transforms of. Remember, using number 3, this one just becomes t. And now this is little x of t. This was big X of s, but now we're taking the inverse transform of both sides. This next one is going to be 2 times using number 5 sine a of t. A is just 1 here, so 2 sine t. This last one is the one that can get a little more confusing. We're looking at number 13 on the sheet, because we have our e to the negative cs. Here c is equal to 2 pi. And then our big F is the rest of this function, so it's the 1 over s squared plus 1. We'll go ahead and write our u term first. So u sub c, u sub 2 pi. You could also write that as u of t minus 2 pi times little f, so the inverse transform of what's left of our function. So we have our function is 1 over s squared plus 1. So looking at our sheet there, that's our sine transform again. So that would be sine of at. A is just 1. But looking at number 13, the inverse transform is little f of t minus c. So this has to become t minus 2 pi. We can go ahead and rewrite this again as t minus 2 sine t plus u sub 2 pi. And then because sine is periodic with respect to 2 pi, this is the sine of t minus 2 pi is just the same as sine of t. You're just going around the circle again. And now we can go compare this to our answer choices. And this will match option C. I should have written u of t there. I just dropped it. It's the same thing. In number 19, we're asked to find the Laplace transform of this piecewise function. The first thing I like to do is draw these out. So up until we hit 3, we're at 0. So starting from really negative infinity, we're at 0. And then we hit 3. And then we go up to t. So that'll look something like this. And then after 5, we drop back down to 0. So we can write this now as one function using unit step functions. We'll get f of t is equal to, up until 3, it's 0. So we need a unit step function that turns on at 3, so t minus 3, because once t hits 3, this will become times 1, or just 1, and then 1 times our term t, because that's where we have to jump up to. But then once we also have hit 5, both of these functions will now be on, because we'll put a u of t minus 5, so that also has to be of t. And we're subtracting that because we'll have a plus t and a minus t, which will bring us right back to 0 there after 5. We can go ahead and take the Laplace transform of both sides of this now. Starting with our u term, we see that in number 13 on your sheet, we need our little f function to be in terms of t minus c. Here c is equal to 3, and here c is equal to 5. But right now, we just have it as t. So I like to rewrite this to keep it organized as u of t minus 3 times, this has to become t minus 3, but we also have to keep it equal. So t minus 3 plus 3 minus u of t minus 5 times t minus 5 plus 5. If it's easier for you to think about just writing this as t plus 5 and knowing that this is now your new t, that works too. Whatever is going to keep you more organized is fine to do it. We can start transforming this now. Using that number 13 on the sheet, we'll have e to the negative cs. So this first one is going to be e to the negative 3s times the Laplace transform of f of t minus c. So we're taking this in terms of t minus 3. So this is really just the transform of t plus 3. Right, because this is getting absorbed into our new t here. And then we have minus e to the minus 5s times the Laplace transform of this is t plus 5, because we're working in terms of t minus 5 now. And now that we've fixed that there, we can just continue treating this as regular t. We don't have to deal with that offset anymore. So we can transform the other two parts now. Transformation of t is just 1 over s squared, and the transformation of a constant is just the constant over s. And then we'll subtract e minus 5s. And this is times, again, 1 over s squared plus 5 over s. I know the 5s and s's look similar. This is a 5, and that is a 5. We can go ahead and check this. I guess I should write this is still little f of t. Here we've now taken the transform, so that becomes big F of s. And now we can compare this against our answer choices. It's going to be either A or B, just looking at the form. The only difference is this sign, and the negative is correct. So answer choice A. I wanted to add this on to problems like number 19, because these confused me a lot with the whole getting your form of t minus c in there. One thing that has been helpful for me is to define a new variable, q, as t minus c. So in a problem like we were doing before, where we have u of t minus 3 times t, q becomes t plus t minus 3. And then we can solve for t is equal to q plus 3. And then you get this e to the negative 3s. And then I like to treat this as the Laplace transform of, we can go ahead and plug in this t there. And then take this Laplace transform as if this q is just t. Just pretend that's the variable t when you're looking at your table. And that'll get you the same result as splitting it up like this. This would just help me stay organized sometimes. Just don't try to then go back and substitute in for t. Just go straight to s and don't look back at any of this. If it's helpful, use it. If it's more confusing to you, then ignore everything I just said and do it whatever way works for you, like we did up here. It's ultimately the same thing. Number 20 is asking us to find the Laplace transform of this function, f of t. The first thing that we need to do is recognize that this is the convolution of two functions. So this is the convolution e to the negative t cosine 2t convoluted with sine of t. Then need to remember the product and convolution properties of Laplace transforms. So remember Laplace transform of, we'll call it f1 convoluted with g1 is equal to the Laplace transform of f1 times the Laplace transform of g1. So this, we can call this f1 and we'll call this g1. We see here that in order to take the Laplace transform of all of this, we can separate it into the Laplace transform of f1 and the Laplace transform of g1 and multiply those. So we will do Laplace transform of e to the negative t cosine 2t times the transform of sine of t. And now this will get us big F of s is equal to, go to our Laplace transforms table and find one of this form, e to the negative t cosine 2t. That's going to match number 10 on the table. Here, a is equal to negative 1, and b is equal to 2. So just copying the form from the table of transforms, we'll get s minus negative 1 is s plus 1 over s plus 1 squared plus 2 squared is 4. That times the transform of sine of t, which is, in this case, a is just 1. So that will be 1 over s squared plus 1 squared. Now all we need to do is substitute in what they're asking us to find. So they're asking us to find big F of 1. If we plug 1 in for s, we're going to get 2 over 2 squared plus 4 times 1 over 1 plus 1, 2. That is 2 over 8 times a half. That is 1/8, and that matches answer choice C.